This lesson is about the work that friction does on a moving object. We really haven't looked at friction yet. In fact, when we looked at our roller coaster, we kind of assumed that there was no friction. But of course, there really is friction in the world. And we're going to take a look at the work that that can do on a moving object in this lesson. So let's start with something that you should know how to do already. On the board here, I've got a sample problem that shows a box of 30 kilograms going down a couple of hills, and we can find the velocity at the bottom. So what I'd like you to do right now is take a second to find that velocity. What would the velocity be of this box at the bottom of the two hills? Now let's add friction into this. We haven't done that, so let's see what that looks like. And for now, we're going to look at the friction in just one spot. We're going to say that there's friction right in the middle here. How about in this area? We'll say there's friction only right here. We'll assume the rest of it has no friction still, because again, we're kind of easing into this. So let's say that this distance here is 3 meters. So there's friction for 3 meters, and the force of that friction, we'll say, is 20 newtons. How would that change things here? What would that do to the box as it goes down? Would it increase the energy of the box? Would it decrease the energy of the box? Is energy allowed to increase or decrease? Now, I think most of you would say that the box slows down as a result of that friction. So where does the missing energy go? Because we know we can't lose energy. What actually ends up happening here is an important thing to figure out. And one of the things that happens is it does really slow this down. How do you figure that out? Well, this is what you would do. The first thing I would do is I would find the potential energy of this box at the top. Potential energy equals mgh. So when you plug your numbers in here, you have a mass of 30 kilograms times g times the height, which in this case is 4 meters. Now that's the total energy of the box at the beginning. That's all potential energy. And so if you put that into your calculator, hopefully you get the same thing I did, and that is 1,176 joules. That's the energy that I start with at the top. That's the total energy. We know that that energy must remain throughout this entire process. It's got to be in the system somewhere. Well, right in the middle here, friction does work on this box. How much work does it do? Well, I can figure that out using the force and the displacement. So if I do that over here, I'd say the work of friction is the force of friction times displacement. So in this case, that's 20 newtons times the 3 meters, for a total of 60 joules. So what do we do with that 60 joules? Well, it started off with this much energy. The box has that much energy at the beginning, and then friction takes away 60 joules of energy. So what are we left over with? Right here at this point, we're left over with this much energy minus that energy. So I'm going to even label that on my picture. I know that the energy there is equal to 1,076 joules minus 60 joules. And that, of course, equals 1,116 joules. That's the energy that I have at that point. Now, what happens to that? Well, all of that energy turns into kinetic energy in the end. So if I do kind of like what you did before, I assume, you just take this energy and find the velocity from there. I'm going to leave you to do that on your own. I want you to find this velocity knowing that there's friction in the middle. And of course, we would expect your answer to be less than what you had for when there was no friction on this. That's a sample problem of how friction does work on an object, and we'll do some more of those types of problems in class. Some as easy as that and some more difficult.